Okay. The next question is this. Suppose you're doing a photoelectric effect experiment and you find that the stopping potential is 1.25 volts. And the question is find the maximum kinetic energy per electron and then the speed of an electron, of each electron. Meaning this, here's what I mean. So this is the next example. So you shine light on a plate, right? Shine light, so you have electrons now moving this way with a certain speed. And what you do is you want to stop them. So what you do is you do this. This is the plus end of the battery. And you increase the voltage so that when they make it here, they barely make it there. So that's 0. So that means they start with some kinetic energy, but by the time they reach that plate, they have 0 kinetic energy. And so we get this. Their kinetic energy is their charge times V. This E here is the magnitude of the charge. So if the stopping voltage then the kinetic energy is equal to the charge of an electron times the voltage. The charge of an electron is E, and the voltage is 1.5 volts, right? So I can write this in EVs first. So it's simply 1.5 electron volts. It's really simple. So with EVs, it's a convenient unit. 1.6 EVs. We can change this to joules. Who can tell me again what to do?
We multiply by 1.602 times 10 to the negative.
Joules for every 1 EV, like so? Yeah. So this goes away. And 1.6 times 1.5. Let's see what we get. I actually don't have that. Oh, I'm sorry. Yeah, that's fine. Let's just do this one. The example I have is 1.25 volts. It was 1.2. We did 1.5, so let's just do it. Can someone tell me what is this? Is it 2.4?
2.4
times 10 to the minus 19 joules, right?
Yeah.
Good. And the reason for the 1.25 would have gotten 2 for 1.25. Would have been a nice number. But that's okay. We have calculators. And we know 1/2 mv squared is equal to the kinetic energy. So the speed will equal twice the kinetic energy divided by the mass. The mass of an electron here. By the way, this little v is the speed, okay? Not the potential difference. You get 2, and then 2.4 times 10 to the minus 19. Everything should be SI units. So joules, mass. And you take the square root of this. Let's find their speed. Anyone? Should be something times 10 to the 5th, I believe.
It's 7.26 times
7.26. let me just do 7.3 times 10⁵, right? Meters per second. I usually go with 3 or 4 sig figs, but it's okay. It's good enough. All right. So let's go back to this. Now, the kinetic energy, because the next problem is we're going to graph something, or it's going to have some to do with some data. So let's say you send a photon and it has a certain amount of energy. Now, will the energy of the photon, all of it, become kinetic energy? Is the energy of the photon, when absorbed by the electron, is it all going to be converted into kinetic energy? Or no? I said yes or no?
I'm guessing yes.
Yes, okay. And it would be yes if the electron is free, if it's not bound to that metal. But remember, we needed a certain amount of energy to break it loose, right? We needed a certain amount of energy to break it loose. So what happens is, the energy of the photon minus the energy needed to break the bond is equal to the kinetic energy. Does that make sense? So the energy of the photon, which is hc over lambda, which is, let me write it this way. The energy of the photon, which is hf, minus the energy needed to break the bond. What should we name it? It has a specific name, but I can tell you. What would you name it?
BB.
Bond energy, something like that? Yeah, okay, yeah. You could. They already chose a name called phi, and this phi is called the work function. The work function is the energy needed to break the electron loose. Okay? So this is called the work function. So it's an energy, and that equals to the kinetic energy of the electron, right? That equals to the kinetic energy of the electron. But the kinetic energy of the electron, usually you don't measure the kinetic energy of the electron directly, you measure the stopping voltage. So the kinetic energy of the electron is equal to EV, the charge of the electron times the stopping potential. Times V. Let's solve for V. Like so. And if you like, we can write this as hc over E over lambda, because hc over lambda is F. I'm sorry, c over lambda is F minus E over E. Okay. Do you see the logic here? How we got to that point? So that's called the work function. Each metal has its own work function, and it has some numeric value. So I'll give you some work functions. Aluminum. To free an electron from the surface of an aluminum surface, you need 4.3 EVs. Okay, so these will be given to you if needed. So the work function for aluminum is 4.3 electron volts. Carbon, 5. Copper, 4.7. All of these numbers are in EVs. Gold, 5.1. Nickel, 5.1. And so on. Sodium, 2.7. Okay. So each metal, each material has a different work function. So, but you see, it's on the order of a few EVs, right? 3, 4, 5, 10 EVs. Okay. So let's work with some data. Here's what we're given. You do the photoelectric effect experiment. and you find the following. Here is the stopping voltage. It's in volts versus the wavelength, which is in nanometers. Here are the data that you get. 1 volt is needed if the wavelength is 600 nanometers. 2 volts are needed if the wavelength is 400. 3 volts are needed if the wavelength is 300. Yes.
4 volts at 250.
I don't know. It's non-linear actually. Yeah. It's 1 over. Let's see. We're going to check this out. You see, it's non-linear. We do this all the time in lab, right? Let's say if I plot the voltage on the y-axis and 1 over lambda on the x-axis, then I get a linear fit, right? So I get. So if I'm referring to this equation. Let me write it. So here's V is equal to H C over E times 1 over lambda minus E over E. Then if I plot this on the y-axis, I'll just have y is equal to something times the x-axis. So 1 over lambda is x, and then plus b, which is the y-intercept, right? This is b, which is the y-intercept. So this is the y-intercept. So the slope, when we plot this, when we plot v over versus 1 over lambda, the slope is hc over e. Okay? The slope is hc over e. So I'm not going to plot it, but we'll just calculate the slope. Okay? We will calculate the slope. So slope is changing y over changing x, right? Delta y over delta x. I can choose any 2 points I like. I can choose the first and last points. Okay? I just choose the first and last points. So let's get the slope. By the way, the goal of this problem is to calculate h, which we already know, 6.626 times 10 to the minus 34. We're trying to experimentally determine h, and we're trying to find phi. So for this problem here, so we're trying to find h and okay, that's what we're trying. So let's do that. So first, h, we need to find the slope. So the slope, as you know, is the change in y over the change in x, the rise over the run. The change in y is, let's choose the points, let's say the first and last point. Okay, the first and last point. So 3 minus 1. So 3 minus 1 over, what am I plotting? What's on the x-axis? Lambda or 1 over lambda? 1 over lambda. So it will be 1 over 300 times 10 to the minus 9 minus 1 over 600 times 10 to the minus 9. Okay? Yes? Okay. So this becomes, let's see if we can do this. We get 2. The 1 over 10 to the minus 9, 10 to the minus 9, it goes upstairs, it becomes 10 to the 9. I'll just write it upstairs, 10 to the 9. Over 1 over 300 plus 1 over 600. You can write this as 2 over 600. 2 over 600 minus 1 over 600 is just 1 over 600, right? So 1 over 600. Let's flip this, it becomes 1200 times 10 to the 9. Or 1.2 times 10 to the 12. What are the units? Volts times meters. Volts times meters, right? Because it's the y is volts, and then the x-axis is 1 over meters, so you get volts times meters. So that's the slope. Now, how is the slope related to h? Well, it's hc over lambda, hc over e, right? So the slope, right here, the slope is equal to hc over e. So we get, let's see here, h then, h will equal to the slope times e over c, right? So h would be the slope times e over c. The slope is 1.2 times 10 to the 12 volts times meters over, we said the slope times e. E is 1.6 times 10 to the minus 19 coulombs, okay? And then over c. C is 3 times 10 to the 8 approximately meters per second. So cancel meters here. What's a joule? What's a volt? A volt is a joule per coulomb. Remember, joule per coulomb from electricity. So it's a joule per coulomb times coulomb. So you're left with a joule. A second flips and goes upstairs, so you get a joule times second. So the units do work out. So you get h to equal to something, and then joules times second. Did I make a mistake here? This one here, yeah, I actually did make a mistake. 10 to the minus 9, when it flips, it goes upstairs, it's actually 10 to the minus 9 still. Because we're multiplying by the reciprocal, so it's 10 to the minus 9, sorry. I just know this because otherwise I'm getting the number that's really big for this. So 10 to the minus 9, 1200 times 10 to the minus 9, you get 1.2 times 10 to the minus 6, sorry. Yeah, 10 to the minus 6. So 10 to the minus 6. Okay. I think now it works out. Minus 6, let's see. Minus 6 minus 19 is minus 25. Minus 25 minus 8 is minus 33. And you're divided by slightly more than 1. This number will be slightly less than 1. So yeah, it would be 10 times 10 to the minus 34. So, anyone can tell me what is this? 1.2 times 1.6 over 3? Should be 6 point, how much?
6, 2 6 is what it should be, right?
Mm-hmm.
Let me see.
6.4? Okay,
Yeah.
sounds good. Yeah, 6 point, yeah. Yeah, sounds good. So that is that. Now the last one, I didn't anticipate this one to take that long. The last one is this. Is what's the work function? How do you get the work function? Well, the work function is, if I find the y-intercept, it's equal to negative the work function over e, right? So how do I get the y-intercept? Well, we know that the slope, you can just use the point slope formula, right? So it would be, let's say, y minus 3, or let's just use the first one, y minus 1 over x minus 1 over 600 nanometers, 600 times 10 to the minus 9, like so. Okay. The slope is this, so I have 1.2 times 10 to the minus 6. By the way, this is what you would be doing if you do the photoelectric effect experiment. Over y minus 1 over x minus 1 over 600 times 10 to the minus 9. Cross multiply, and you get y minus 1 is equal to 1.2 times 10 to the minus 6 times x. This one is fine. And then multiply this, you get minus 1.2 times 10 to the minus 6 over 600 times 10 to the minus 9. Yes?
Yeah.
Okay. And then move the 1 to the other side and you get y equal to 1.2 times 10 to the minus 6 times x is equal, when you move the 1 to the other side, what do you get? Let's see here. This becomes 1200 times 10 to the minus 9, so it becomes minus 2 plus 1 becomes negative 1. Negative 1. Yeah, just negative 1. Okay, sounds good.
Negative 2, I think.
But I moved 1 to the other side, so
Oh.
it's plus 1.
Yeah, you're right.
So we get the following, we get this. Negative phi over e, that's the y-intercept, is equal to the y-intercept that we just found, is equal to negative 1. That means phi will equal to just e, which is 1.6 times 10 to the minus 19. Since this one would be in volts, it would be EVs, electron volts. It's technically E times 1 volt. E times, but this number here has a unit, it's 1 volt. So it's the charge times 1 volt, and so you get that. All right. I think that's good enough for these photoelectric discussions. I'm going to erase the board and then we will discuss the next topic, which is the Compton scattering. But before then, Compton scattering, usually you send, for the photoelectric effect, usually you send the incident light will have wavelengths corresponding to visible light or UVs, okay, or UV light. Usually it's done with, you have a mercury lamp and it sends UV light and you use some filters, and those filters will allow just a certain wavelength through, and then you do your experiment. You find the stopping voltage for, let's say, 600 nanometers, 400 nanometers, and 300 nanometers, just like that, and then you plot it, and then you get, you analyze your data and you find H, or the work function. Now, the other thing is, how do we produce X-rays, right? How do we produce X-rays? So it was discovered by accident in the late 1800s. And so when people knew that accelerating charges, they emit radiation. The charges that accelerate, they emit radiation. And that radiation could be in the visible range, that's light, or just visible light, or it could be infrared or some other wavelength. So what they did was accelerate in some vacuum tube. They accelerated electrons to really high speeds, and then those electrons, they strike a wall. And when they strike a wall, they just come to a stop really quickly. So they hit the brakes really quickly. And when they stop really quickly, that's a very large acceleration. And that acceleration causes the charges to emit X-rays. X-rays happen to have wavelengths in the wavelengths of about, I remember this because X-ray diffraction. You find the structure of materials, and so how far are atoms from each other? You're talking 10 to the minus 10 meters. So X-rays would have naturally around wavelengths of 10 to the minus 10 meters, or a tenth of a nanometer, maybe 0.2 nanometers, maybe 0.5 nanometers, maybe 0.1 nanometers, something like that, somewhere in that range. So let's discuss this Compton scattering.